2014 walkthrough, and we have a 21 through 30 lined up. So starting with 21, the molar mass of iron is 55.85 grams, so we're essentially reacting 1 mole of iron. So it's 1 mole of iron with 1 mole of oxygen, and the enthalpy of formation of ferric oxide, I think that's how you would say it, is that number. The one tricky thing is that we're talking about the enthalpy of formation here. Enthalpy of formation means you make 1 mole of a compound from its constituent elements. The 1 mole part is the tricky part, because we're making 2 here. So we're going to need to multiply this enthalpy of formation by 2 to actually get the change in enthalpy of this specific reaction that we're looking at. But before we calculate that out, we actually won't have to. Let's just see what we have to do next. So, like I said before, 1 mole with 1 mole, iron's going to be the limiting reactant. Basically, we're doing this reaction, but in 1/4 of its ratio, because 1 divided by 4 is 1/4. So actually, we're going to multiply by 2 and then multiply by 1/4. So we're basically going to end up halving this number. So that's why we would come out with 413 kilojoules released. Number 22, heat capacities are given. Oh, okay, so this is pretty easy. Basically, higher heat capacity, you can absorb the same amount of heat without rising in temperature as much. So just using that definition, iron should rise in temperature the least. Oh, sorry, I'm reading this backwards. So what I said was true, but also you will lose the same energy without going down in temperature as much. So same concept, just applied in the opposite direction. So because it's the metal that was heated this time and not the water, you would expect iron to be still at the highest temperature because it lost the same amount of energy without feeling that change temperature-wise as much. So that leaves you with B and C as choices, and PB has the lowest heat capacity, so it would be leftmost in this inequality. 23, the enthalpy of formation is 0 for what in their standard states? That's just elements. Yeah, I mean, that's just part of the definition of it. So, just something you should know. What are the signs for these things? So the key thing here is that this thing occurs. So if it occurs, it's spontaneous, so it's not A or B. Because spontaneity is determined by a negative Gibbs free energy change. So, okay, you're going from a liquid to a gas because you're injecting something into an oven at 400 K, which is above 100 Celsius. So your entropy change is going to be positive. Your enthalpy change is also positive because you're inputting heat that disrupts the hydrogen bonding of the water and makes it go become a gas. So that's why you have C. A device used to test alcohol uses this reaction. Okay, so this has absolutely nothing to do with the rate law. If something disappears at a rate, it's only determined by its coefficient. And something else disappearing or appearing at a different rate is also just determined by the coefficient. So the coefficient on potassium dichromate is 2. The coefficient on, what is that, ethanol is 3. So you're essentially going to multiply this given value by 1.5. So that'd be 0.62, 1.6, or 1.86. So that's why you get C. 26. Okay, so it's Le Chatelier. Okay, not necessarily, but we can treat most of it as Le Chatelier. So if you decrease the temperature, it's endothermic, right? Because we have a positive delta H, so we can say heat is a reactant, so we can add it over here. Decreasing this reactant will drive the reaction left to replace it, so that's not going to increase our reaction rate. Decrease the partial pressure of CO. I mean, yeah, that would drive it right. Decrease the partial pressure of CO2. That would drive it left. Okay, so basically, what I'm doing right now is a very flawed understanding of this, because right now I'm talking about equilibrium states. Like I'm talking about how present each substance will be at equilibrium. It's generally a decent indicator because you can't shift the reaction left and have it go faster forward, if that makes any sense. So that's why we could eliminate B and D based on that, but we can't eliminate C. The reason it's A is because if you decrease the size of the graphite pieces, you're increasing the surface area of the entire thing, which means that the catalyst has more places to interact with, and more of the participating molecules in the reaction are able to undergo that reaction pathway that has the lower activation energy, which increases the rate of the reaction. So that's why it would be A. This reaction is first order. Which characteristic changes as it proceeds? Just by definition, reaction rate, because reaction rate will be dependent upon the concentration of the reactant, because it's first order. We can just look at the other stuff. First order, half-life is just ln2 over K, and K will remain the same for a reaction at a certain temperature, so it's not it. Rate law, same thing as K. It's the same, actually not the same thing as K. It doesn't even matter about the temperature. It's just the same for one reaction. Rate constant, I just talked about that, so it's not B. So it's D. Okay, so these types of problems are quite common. They're just the simple kinetics problems. If you compare trials 1 and 3, A is held constant, B is doubled, but the rate does not change, so that means it's not affected by a change in B's concentration. So anything that mentions B is just wrong, so that's why B and D are not right. And if we look at 1 and 2, B is held constant, A is doubled, the reaction rate actually quadruples, so 2 to the second power is 4, so that's why we'd have C. 29. First order reaction. Okay, so Arrhenius. This is what the Arrhenius equation is. I mean, this is when you're comparing a reaction's progress at two different temperatures, basically. I guess there you can rephrase it. So basically, ln K is equal to negative activation energy over R times 1 over T plus some constant. So if you plot ln K versus 1 over T, basically you're going to have a y equals mx plus b equation. What I just circled is going to be your m, this is your b. So circle is the slope, and then c is the y-intercept. Yeah, so that's how you get the definition for the activation energy. Okay, number 30, there's our last one. What about a catalyst is correct? Reacts with the product and shifts the equilibrium. No, does not affect equilibrium concentrations. Lowers the active. No, it does not take the original pathway. Provides additional energy. That's already kind of fishy. No, it's not providing energy. It's just offering a different pathway to take, which is what 30D describes. So next time we'll do 31 through 40. Good luck.